First, I want to welcome all of you to join this 2022 Loess Early Career Researchers Workshop. And the first, we would like to invite Professor Shilin Yang to give us an opening remarks of this workshop. Professor Yang, please.
Okay, hi everybody. Good afternoon, good morning, Dr. Xu Zhiwei, Dr. Aditi Dam, fellow speakers, and good afternoon, good morning to the workshop participants joining us online from around the world. I'm Shilin Yang from the IGG CES. Welcome to the Loess Early Career Researchers Workshop. I'm so happy to tell you that we have 32 registered participants from 8 countries, including Finland, India, Russia, Sweden, Tajikistan, United Kingdom, USA, and China. Today and the next 4 days, 5 distinguished colleagues, including Drs. Yang Pieter Buylaert, Peter Worms, Gamber Urari, Samuel Albani, and Lu Huayu, are going to talk about recent advances in various aspects of Loess deposits. On behalf of the Loess Edgepadal Stratigraphy Working Group, I'd like to thank Dr. Xu Zhiwei for organizing this ECR workshop, and each of our speakers for taking part in this event. I think the quality and caliber of speakers this workshop is very outstanding. I also want to thank all of you for connecting this afternoon. But I hope you are looking forward to keynote talks and discussions as much as I am. The Inquan Loess Working Group has a very, very long history. It was founded in 1961 at 6 Inquan Congress in Poland as an Inquan sub-commission. It was upgraded to full Loess commission status in 1969, while in 2003, the sub-commission was re-established and later was changed to Loess Focus Group. 2 years ago, it was renamed the Loess Edgepadal Stratigraphy Working Group. Over the last 60 years, a considerable amount of activities have been organized, such as Loess Fest, regional Loess science meetings, field trips, and newsletters. And both areas and topics of Loess research have been extended. During the early stage, the aim of the Loess Commission was to study Loess stratigraphy over Europe and to develop continent-wide correlations and mapping. Today, the research topics are more wide-ranging, including modern observations, numerical modeling, provenance tracing, and paleoclimate analysis. It's no exaggeration to say that Loess deposits are one of the best terrestrial paleoclimate archives. I'll never be so proud that our Loess Commission has become one of the most successful and long-lasting Inquan working groups. I think students and young scientists are the future of our Loess community. I hope this workshop serves to inspire more and more young people involved in research on Loess and to build collaboration among Loess researchers worldwide. And finally, I wish you a very successful workshop. Please join us later at the Loess Fest 2022, which will start on August 20. Thank you. Thank you all.
Thank you, Professor Yang, for your warm and very kind opening remarks. We are very pleased and we are happy that we can organize this workshop and bring these early career scientists together to learn from the established and senior scientists. So today will be our first lecture, which will be given by Jan Pieter. Jan Pieter is is a senior scientist. He's have many years experience in luminescence dating. So he will give us talk on recent advances in geochronological method. So to save time, let's just welcome Professor Jan Pieter to give us the talk. Jan Pieter, please.
Okay. I will share my screen. So, yes, thank you, Dr. Shu, for your very kind words to me. And I would like to also express my gratitude to invite me to this workshop. And as I said before, I am a little bit twitchy to give my presentation today because it's always hard to pitch it right for early career researchers because they know so much already. And maybe the level will be a bit too low in some parts and a bit, and I may be right in other parts, but I'll do my best to give you some interesting insights in luminescent chronology. Because the talk will mostly be about luminescence dating, because that's essentially the technique I'm most familiar with, and also that's, in my view, the most powerful one to date Loess. So, as I said, as I was introduced, I'm part of the Technical University in Denmark here, and most of you know this as the RISE laboratory, RISE Luminescence Dating Laboratory, and that exists already for about 40 years now, so it's a long-lasting lab. But now, just let's get going. And what do we actually try to do in Loess research? And we measure many proxies as a function of depth here. And for example, here you have the magnetic susceptibility, you have the mean grain size here, you have source, you have Loess, you have interstadial Loess here. And this is shown here from Kang et al. In the southern part of the Chinese Loess plateau.
I can't see your screen.
Sorry. This is typical for me. Share screen. I'll start again. Sorry, this is not the first time it happens to me. So, what do we try to do in Loess research? What you guys try to do is basically you measure many proxies, grain size, isotope ratios, magnetic susceptibility, and you measure it as a function of depth. But what we want to do is essentially we want to get this from a depth scale to an age scale. And why do we want to do that? Because we want to compare our records. We want to compare it with some more regional records or with more global signals. For example, here these are the oxygen isotope stage ratios from the Hulu and Sambao caves, so the stalagmite records, or more a global signal here from the deep sea. And that's what we want to do. Essentially, sometimes at a certain location, we also have multiple sections that we have excavated, and we also want to be able to correlate them. And there also chronology is very important. Now, we all know there are correlation-based age models. And what is it actually? There's a great similarity between, say, magnetic susceptibility or a grain size record and the marine delta 18 record. And what we can do to derive chronology is to wiggle match these records and then find some tie points between the two records, and in this way construct an age model. But there are some very important assumptions there. One assumption is there cannot be any discontinuities in your record, and you need a constant sedimentation rate between your tie points. And of course, you can't, because you're tying one record to another, you can't really look at leads or lags between different climate systems. So what has been shown that on orbital timescales and inside like stable geomorphological settings, for example, the famous Loess 1 site in central part of Chinese Loess Plateau, that this is essentially applicable. You can get broad and good chronologies based on correlation-based age models. But what about shorter timescales or sites prone to erosion? And I would like to give you some examples in the following slides. Now, this is data from Stevens et al. In paper in 2008 for the Baigo 1 site in the central part of the Chinese Loess Plateau. And you can see here that two different kinds of age models, one correlation-based and one independently dated, gives quite a different result. So the bottom part here, the bottom age model here is a correlation-based age model, and the top one is based on luminescence dating or on optical dating. And you can clearly see that It's more that the correlation-based age model gives older ages towards the end, toward the deeper part of the section, and younger towards the top part of the section. So also it cannot capture this hiatus here that is found in true optical dating. So there can be significantly an error at these kind of millennial timescales, these correlation-based age models. Now, another example, slightly more dramatic, if you go to the northern edge of the Loess Plateau, this Jinbiang site, a very important site in the Chinese Loess Plateau, you're much closer to the deserts, you're much more in a dynamic environment. And what we did there is that we took 5 sections, and you have the magnetic susceptibility plotted to the right always, and the age model based on optical dating next to it. And as you can see, what is immediately obvious is that you get gaps in the record, hiatuses from up to about 50-60,000 years. And what's also interesting to notice, what we found there is that you actually have some older Loess sitting a bit higher in the landscape than your Holocene soil here at the S0. So this means this is quite a dynamic landscape, and then you have a Holocene soil that has developed inside a gully. Also, maybe less visible here, you get some sedimentation rate changes here that are quite clear, and that's of course only achievable through an independent dating method. So if we would have tried the correlation-based age model here, there's very high chance that we would have gotten it wrong. Now, the last example that I'd like to show you, because it's a paper that's going to come out very soon now, is from the Volga region. There's a lot of Loess around the Volga River. The Volga is a major Russian river that is discharging into the Caspian Sea. You have beautiful Loess paleosol sequences alternated with lacustrine sediments and with more alluvial clay sediments here. And there has been major debate in Soviet times and also quite recently, how old is this Loess and how old are these different soils here? And it varied from, okay, everything is stage 3 here. These are interstadial soils, and this is stage 5, and then this is stage 6, stage 7, marine isotope stage 7 or 9 or so. So there was a major debate, and only until we were able to date this in great detail with, I don't know, we have probably about 50, 60 dates here, we were able to settle the debate. And it's quite clear that this is soil marine isotope stage 5 sea soil, and this is one developed during marine isotope stage 5A. And the ages are a bit older than A and C because they have developed into the Loess that it's underlying, underlying the soil. So you get some pedogenic overprinting. That's always important to take into account also. Then in the field, they were able to identify a little erosional boundary here, and also our age model is consistent with a small gap of a few thousand years here. Then you had the rapid sedimentation here of these clay sediments. And that's basically the Caspian Sea that has transgressed over the landscape there and has deposited all this clay in the period from about 25 to 14,000 years. And then you have the Holocene soil on top. And you can immediately imagine that it's not easy to get this kind of information just by correlation-based age models, because it's quite a detailed chronology you need for that. Now, this is just a slide. So independent numerical chronologies are necessary to correctly interpret and also fully exploit the Loess proxy record. What do we have available? And this is a figure I modified from Aitken et al. in 1998. And it's basically for dating methods in the Quaternary. And what you see here, it's a logarithmic scale, and each method has a certain color. And the wider the band is, the more applicable it is in Quaternary dating methods. So as you know, radiocarbon dating is quite often used, cosmogenic radionuclides as well, luminescence also. Cosmo in Loess is of course not frequently used or even not used at all. So, and you can see here some under the radiometric dating methods, you have potassium argon, and fission track and so on. Very important methods, but for us in Loess, you need a tephra, right? So that's hard to find. There are some good marker horizons, but they are essentially sparse. And so mainly what we have is radiocarbon dating and especially luminescence dating to get chronologies in Loess. Note it's a logarithmic scale, and what I should also add is that the color when it's changing towards the younger and the older end is because that's where you're pushing the limits of the techniques. So let's first have a look at radiocarbon dating, because there are two very important studies that have been carried out there. But as you all know, there's abundant evidence. If you do bulk organic matter or soil carbonate, you get very often age underestimates. And but in two recent publications, they have shown that excellent chronologies could be derived if one can extract charcoal fragments or small mollusk shells, or like small gastropods, or earthworm granules from Loess. And this you can extract through some wet sieving at about a 500 micrometer sieve. So this is from Ujvari et al. Here, some L1 Loess in Dunajecko in Hungary. And you can see here some charcoal fragments they collected from here, and then different kind of gastropods. And what's important here to remember is that not all mollusk species are actually suitable for this radiocarbon dating, because you need to have, they don't bury themselves deeper in the Loess, and also they should not feed on old carbon, or you get age overestimates, of course. So you need somebody to identify the species for you, so you get the right ones. In those publications, you can find which ones are work best. And then another nice study was from Wan et al. In 2017, where they looked at dating of earthworm calcite granules from Nussloch, the famous Nussloch sequence in Germany. And what are earthworm granules? Calcite granules, they are essentially, this is poo from earthworms. Can go up to about 2.5 millimeters in size, and has like this ovoid shape. And it has a high abundance in soil, but it's nearly absent in Loess layers. So this is also an assumption. This has also been investigated, that these earthworms, they can of course not bury themselves, and looking at recent earthworm behaviors, they stay in the upper 10, 20 centimeters in the soils, and they only feed them on upper litter, so they don't really feed on old carbon. And this is an example from one of these beautiful age models here, from about 35,000 to 24,000 from Dunajecko site, from Ujvari et al. You can see you can get a very precise age model. They have some charcoal ages that agree very well with the mollusk ages. And I think this is one of the best examples with 150 radiocarbon ages. So a very detailed and precise age model. Now, what I see as the challenges in C14 dating and Loess is usually you have a low abundance of datable material. So it's not applicable to all the Loess sections. We try to get these earthworm granules from the Lodge 1 Loess sites, from the L1. We had thick slabs, took huge samples back to Denmark, and we had a student sieving for many, many days, and he couldn't find any. Also, we've been looking for charcoal fragments in some of the Volga Loess sites, and we couldn't find any suitable charcoal there for dating. So you need to sieve large samples, and it's not always possible in the field. This is essentially time-consuming to do. And if you want to bring the whole thing back, it's going to cost you a lot of money. So the shipping costs are quite large. So now, in any case, we are limited to, say, the last 40,000 years in radiocarbon dating, perhaps 50,000 years, a bit longer, depending on who you speak to. So that's not a very long part of the Loess records we can look at. More comparisons of C14 ages from different materials is what I would like to see, at least in the future. Because now we have these two studies I've just mentioned. There are probably a few more. But what is really the difference between a charcoal age and the one that you get from the gastropods from the same layer, to get a bit more information, the precision and accuracy of radiocarbon dating in Loess. So, because we all know you can get extremely precise radiocarbon ages, but when you do it from the same layer and different kind of source materials, do we still get the same? Do we get the same age, or do we get more of a dispersed data set? That's something that would be nice to investigate a bit further. So now let me move on to luminescence dating. And most of you know this very well, and I'm not going to go in great detail, but those of you who don't know, it's a trap charge dating method that measures when sediment grains were last exposed to sunlight. So you're dating the last time quartz or feldspar was exposed to sunlight. It's widely applicable to many, many different kinds of sediments and even rock surfaces these days. You get an age in calendar year, so there's no calibration curve, but what's important is the uncertainty is at best 5%. So if you see a luminescence age that has an error that is smaller than 5%, you should be a little bit suspicious. There are many systematic factors going into luminescence dating that prevent you to go better than 5%. And this is a relative error. So when you have an age of 100,000 years, the uncertainty is at least 5,000 years. If it's 1,000 years, it's 500 years, and so on. So we need to take that into account also during the sampling process. But it has a wide dynamic range from a few years and can go to several hundred thousands of years. So it's quite powerful. Now, a little bit on the principle, acquisition and loss of luminescent signal. Imagine you have some mineral grains in the rock and sandstone. It gets eroded, and it gets into a river system, or it's wind blown, and it gets exposed to sunlight. It will lose its luminescent signal. It will lose its electrons that were trapped at defects in the crystals will be released. And upon the release of these electrons, a small luminescent signal will be released. And you're essentially losing this luminescent signal. So the the luminescence clock is reset there. It gets buried again. It can build up again due to ambient radiation in the soil or in the sediment. And then again, the same thing can happen again. You can have erosion, transport, deposition repeatedly. So essentially what we measure exposure to daylight bleaching here between sample collection here and the last time it was exposed to daylight. Let's go a little bit more in detail on this energy absorption during burial, because that's quite important for sampling, where I'd like to at least mention a few things. It comes from ionizing radiation, so alpha, beta, gamma decay from uranium, thorium series, and also potassium-40, and reagent sediments from alpha particles. So the helium nuclei is about 10 to 20 micrometer. Beta particles about a few millimeters, and gamma it's about 30 to 50 centimeters. And that's important to know when you sample for luminescence dating. Now let's look at the age equation very simply. We need to determine the dose, so how much energy was absorbed during this burial period, and then you need the rate of energy absorption. And this is where my life comes in, my scientific efforts come into play. Basically, we have all these different signals that I've put here, and there are even more than this. Optically stimulated luminescent, infrared, you have ITL, you have IRF, many different ways to release this charge from the traps. And the way these are different signals you're getting, and you can measure them using different methods. So using single aliquot regenerative dose methods, using multiple aliquot methods, and so on. There's a whole plethora of different protocols to measure dose. And this is where the big challenge lies in luminescent dating. Get it right, get the dose measurement right. In Loess dating, the dose rate is usually quite simple. You measure uranium, thorium, and potassium-40, and you add also the cosmic ray component, which is typically quite very small in Loess, because we have quite a lot of uranium, thorium, and potassium in our sediments, giving us a dose rate of 3 to 5 grains per 1,000 years. But everything is modulated by moisture in our sediment, because that moisture will attenuate the radiation reaching the grains, so you will get lower dose rates if you have more water on average in your sediment. So that's quite an important factor also in Loess dating that we don't particularly have a very good handle on, is what I should also be saying now. So let me move on a little bit to sampling, and I will get back to the dose measurements. Sampling, typically you hammer light tubes into a Loess section, and this is old pictures from 20 years ago almost, where we didn't take so many samples in a sequence in Loess. But typically what you find now is you take a sample every 20 centimeter, maybe even every 10 centimeter. What's also, because of the uncertainty on our ages, you will increase the spacing between samples towards the bottom in your section, because you won't have the resolution on your age anymore deeper down in the section, because it's getting older, and your uncertainty are, as I said, at least 5%. So there's no point in taking a sample every 2 or 5 centimeters when you have uncertainties of at least 5,000 years, or sometimes even 10,000 years. So just for those of you who have not sampled there, sometimes it may be easier to work at night and use some red lamp torch to cut blocks of Loess out of the section at night. Of course, after scraping away some light exposed material. Then I'd like to draw your attention to some So slightly more, and it's more unusual in Loess deposit, but you can have sometimes this alternation of more heterogeneous deposits. You have beautiful Loess, quite homogeneous here, no problem, just hammer in a tube anywhere you like, except when you start to reach these lithological boundaries, because when you come close to lithological boundary, you will have influence from the gamma rays from this maybe more clay sediments to your luminescent sample that you dig here. So you want to either stay away from the boundary, 15, 20 centimeters, so you only have gamma photons coming from here, or you want to take an additional sample so you can model the dose rate, or you want to do some field measurements. And then another thing, as you can see, which we have just also have had some trouble with ourselves, you have some sandy layers in between here in these clay sediments. And if you want to date those for dating, these are millimeter to centimeter thick. They are essentially beta particle thick. So a lot of the beta particles, or nearly all of them, when you try to date this layer here, will come from the sand grains surrounding the grains you're trying to date. So you will need to take a separate sample for beta dose rate determination. I see there's something in the chat. Okay, yeah, yes, questions for later on. So this is quite important that you think about the range of alpha and beta and gamma radiation when you're taking samples. Usually in Loess it's not a problem, but you can have alternations in some more complex settings. So that's what I'd like to mention here. But we should move on. And yeah, I will not spend a lot of time on it, but typically you'll measure fine sand, very fine sand fraction through standard chemical preparation procedures, wet sieving, using HCl to remove carbonates and organic materials. Sometimes it's easier to do HCl and H2O2 before sieving, because then because Loess can be very consolidated. It can be very hard to push through a sieve. So it's better to break up the pieces in water and to add the acids before that. The reason I would suggest to use fine sandy sediments is because it's easier to prepare. It's faster instead compared to the fine grains, and it usually works better also, as you will see a bit later on. Now let's go back to the estimation of the burial dose. So what is the burial dose? We call it in our field the equivalent dose or paleo dose, because it is actually a laboratory estimate of the radiation dose that the sample received during the burial. And an equivalent means that because we are measuring an equivalent beta dose or an equivalent gamma dose based on depending on the type of radiation we use in the laboratory. Whereas in the nature, sediments and grains have received both alpha, beta, and gamma dose rate components, but we essentially regenerate. We using one type of radiation, beta or gamma radiation, and that's why we call it equivalent beta dose or equivalent gamma dose or paleo dose. Now, what do we do? We measure this natural signal during burial, and that's compared with the laboratory signal. And what's really crucial is that to get an accurate age, you need natural and laboratory regenerated signal must have the same identical growth with absorbed energy. And I'm going to try to animate this using this small thing, because that's quite important that you have this in the back of your mind. Okay, when you're measuring a dose in quartz or in feldspar, what am I actually trying to do? And imagine you have a Loess deposit depositing, say 100,000 years ago, and the natural signal will start to grow like this. We don't know the shape of this curve. Normally, we don't know this. All we can measure is the natural signal as we sample it now, like say 100,000 years later. And it has absorbed like this kind of, in this case, 80 gray or so during this burial time. Only when in the laboratory we can regenerate this curve, we can regenerate this growth accurately. It is shown here with the green curve. We will get the right answer. We will interpolate our natural signal here on the x-axis, and we'll get the right answer. But as soon as the growth we are building in nature, in the lab, starts to deviate from this natural growth, you will get the wrong answer. Here you'll get an overestimation because it's saturated earlier. Here you can get an underestimation because we are interpolating always this natural point that we usually don't know on one of our lab curves. And that's important to know. Now let's go now to luminescent dating of young Loess. And in I'm talking about age range, a few years to a few tens of thousand years, basically restricted to the last 3 marine isotope stages. You will use quartz normally, and you use a SAR method, and you will use OSL. And this is what I consider still the state of the art for dating young Loess. You'll try to collect these coarse grains, and perhaps in some cases only fine grains can be extracted. If you have very fine material, fine Loess, it's possible. They usually have a bright and fast component signal. There are exceptions. You can, in volcanic areas, so like in Japan, sometimes you have problems with your quartz that is not bright and fast component dominated, and then essentially you're in trouble, because you can't use quartz that doesn't have a fast component for at least dating with OSL. That is really problematic. Now, Loess, as we all know, it's well bleached, it's aeolian transport, it has had plenty of opportunities to be reset, so we can measure large multigrain aliquots and do simple calculation of an average dose. My experience is you can measure a few tens of milligrays. You can actually look at historical dust deposition, because very small equivalent doses can be measured using quartz OSL. We will measure SAR, and we'll do an early background subtraction. I'll talk about early background on the next slide. And there are many laboratory performance tests that we do to give us some confidence in what we do in quartz OSL dating. We have recycling ratio, recuperation, and so on. I'll give some examples also in the next couple of slides. But the first thing you need to do when you date with quartz OSL is measure your natural signal or a test dose signal, and compare it with a signal of a sample that you know is fast component dominated. And typically calibration quartz that we provide or other laboratories provide, they are fast component dominated, which means that when you start to stimulate with blue light, it will decay within a very small amount of time, depending of course on your light power. But if these two shapes overlap, you are definitely fast component dominated. So that's the easiest way to know whether your quartz is fast component dominated or not. So that's a prerequisite to date with quartz OSL, and that also means that you have to have an absence of feldspar, because if you have feldspar in there, your decay will also become slower. Not much slower, but it will become slower. And when I talked about early background, this means that you will bring your background subtraction as close to your initial integration of your signal as possible, because there's fast component domination, but there are some slower and medium components that underlie this fast component. It's a sum of 3 exponentials that you're having here, and if you bring it closer to the initial integral you're using, you will proportionally subtract a bit more of the slow and medium components. So early background subtraction is now very standard in luminescence dating, and especially luminescence dating of Loess. So I would always advocate to use that. Now, we have many tests that we do. We do a preheat plateau test. We can measure dose as a function of preheat. We can measure. We can also measure the recycling ratio as a function of preheat, and we would like them to show at least some plateau regions, so where the dose does not change as a function of preheat temperature. Typically, what I would use in Loess is 260, 240, but in principle, for this sample, I could use 160 preheat because there's no trend with the dose. And if you are in a new site, I would suggest to do at least 1 or 2 preheat plateau tests to see that it's flat, or to at least find a region where you have a sufficiently broad region where your dose doesn't change with the temperature. The key test is the dose recovery test. And what is dose recovery? You're going to bleach your sample down, so you're going to essentially do what nature does. What nature does with sunlight, you bleach it down in the lab or outside, and then you're going to give it a dose in the laboratory, a dose that you know, and you're going to calculate the measure to given dose ratio, and it should be close to about unity, within 5 or 10% is what we generally say. But although it is the most important test for any SAR-based method, it does not guarantee accuracy. It doesn't mean because your dose recovery is really a very good one that your ages are absolutely right. It's only one of the things that you need to convince your colleagues and the readers that you have the accurate ages. But and I would suggest you read the Nature Primer paper by Murray et al. where we also advocate this. In the end, the ultimate test is with independent age control, but we don't always have this, so we need to do it as good a job as possible in the lab to get this to convince ourselves that we're not making any gross errors, at least in the laboratory. Now, one slide I usually also present is, very often I get the question, do you have to reject aliquots with poor recycling ratios? And so far, I have not really seen any evidence, at least published evidence, that it makes a difference. And what's shown here for Loess site also from China, 461 aliquots from different samples. They're all normalized to the sample average. The dose is normalized to the sample average. And as you can see, even samples with good recycling ratios show quite a bit of spread in dose. And also when you have poor recycling ratio, they're quite consistent with the mean value. So if there would be any significant trend, then of course you could start to advocate for rejecting aliquots with certain recycling ratios. But so far, at least the evidence that I think is published is that it's not really making a difference. And you would actually throw away quite a bit of good data, I would say. Now, some chronologies I would like to present to you. A very nice paper here in 2018 by Xu et al. Closely spaced samples, they give detailed age models. Here for the northern and northwestern side, what you can see is you can get some clear changes in sedimentation rate after about 15,000 years. So like a bit of breaks off and it slows down here towards the Holocene. In the southern and southeastern sides from the Chinese Loess Plateau, they see there's like a little gap here at about 15,000 years, but the sedimentation rate seems to be quite consistent. So what these closely spaced samples and detailed age models can show is that you can detect discontinuities, and you also can look at this changes in sedimentation rates quite easily using quartz-OSL dating, at least, but you have to stay quite young actually. Because this is a tricky one. What is the upper age limit or the upper dose limit for quartz-OSL? And it's a contentious topic, I think, because there is no really clearly defined one available. I will try to give a recommendation here in this presentation. This is some work done by Timar and Gabor and Wintel and the group here there, whereby they date with coarse grain quartz, a Loess site which has a Holocene soil, L1 Loess, and the last interglacial soil. And you can see the fine grains actually deviate much earlier from the expected ages. Coarse grains are reasonably in fairly good agreement, but at least when you get into the soil, you're getting definitely below the last interglacial soil, so the L1 Loess. In the L2 Loess, I'm sorry, you seem to be getting really serious age underestimations. And this has also been shown by Yi et al. This is not with soils to look at the expected ages, but when you compare quartz and feldspar, after about 40,000-50,000 years, you can clearly see that the open circles are lower than the filled circles. So your quartz ages tend to become a bit too young as it gets older, and can get significantly too young. Here we get an age of about 50,000-60,000 years in what they assume is the last interglacial soil, and that's also been dated using feldspar. So a little bit of work also from my PhD. The details don't really matter, but you have the S1 soil sitting here in between these two horizontal lines. If you look at the quartz-OSL signal, the red symbols here, we would definitely expect the red symbol to be older than 75,000 years. And also here, below the soil, you would want to be above 130,000 years. And to give you the extreme case here, when you take a sample below BM boundary here, so at least I think the sample is expected to be 900,000 years old, we got an age of only 110 or 120,000 years. So that's a significant age underestimate. But so you need to be very careful with quartz. And the funny thing is that the curve keeps growing. So your natural signal can still be easily interpolated here. That means there's something funny going on. So my suggestions are 150 gray. It tends to be the upper limit in Loess. And I see I'm running a little bit out of time. Bigger than 150 gray, very often you see age underestimations. But as we see, the lab dose response curve seems to keep growing. What is going on? So, as I said, we can only get accurate ages when the lab and the natural dose response curve overlap, and we can look at a bit more in detail there. how do we build one of these natural dose response curves? And this is where I think the Loess community can help us, the luminescence dating community, to look at upper age limits of certain dating methods, certain signals, and also at stability of certain signals, because it allows us to build some of these, at least to the best we can, these natural dose response curves. So we need some known age samples, you need homogeneous materials, so you don't want any hiatuses, and you need a constant input of material with the same luminescence characteristics. And how does it work? Basically, they assign a reasonable age based on stratigraphy and correlation with the deep sea composite record. This is an example for Lodge 1 here. And then people go, and then this is the first 600,000 years, next 600,000. Back to the whole quaternary tertiary boundary, you can take luminescence samples. And what you can then, they are assigned an age, a certain age. For example, here at the bottom of the S1 soil, you would say, okay, 130,000 years plus or minus, say an error of 10% is good enough for this case. It's important that we don't need to know the age very precisely. We need to know it reasonably well, but it doesn't have to be very precisely. And then you can calculate actually your x-axis of your natural dose response curve, because we can measure the dose rate. And then we know, okay, this sample, we expect the dose in quartz grains to be 420 grays. So then we can measure the natural signal and plot this as a function of this expected dose. And that's what's done here by Chapeau et al. In 2012 for quartz OSL. So this is one of these natural dose response curves. And as you can clearly see, it's completely flat above a couple of 100 grays here. And if they then measure lab curves for different aliquots, you can see that there's only an overlap up to about 150 gray, which is also what we where we start to run into problems. Similar work has been done on another site by Timar, Gabor, and Wintel for both fine grains and coarse grains. And in this case, the natural curve is shown here with the square symbols or the open circles, and the lab curve is actually the solid curve here in red or in blue here. You can again see overlap up to about 200 gray, and here we don't really see good overlap between 100 and 200. Here you will get the right answer at 300 gray, but you will get it wrong. You will get overestimates below that, and you will get underestimates above that. So there's something strange going on there, at least in the study. But it tells you that basically very often this age underestimation is due to a mismatch between natural and lab dose response curves. Now, let's move on. Beyond quartz, we're going to move to post-IRSL dating. As you all know, this has been heavily applied in Loess deposits around the world, and that's because feldspar growth curves show more extended growth compared to quartz growth curve. Here they are normalized to your saturation level, and as you can see, feldspar shows extended growth. Now, and I often get the question, which post-IRSL protocol should I use? Well, it's a balance between bleachability and stability. So if you use lower temperature stimulations or lower preheats, you have a more bleachable signal, but it's going to be less stable. If you use higher preheats and higher stimulation temperature, it will be more stable. And this is shown here for two-step protocols, two-step post-IR protocols, but the same is true for MET protocols. So in my view, usually you will use post-IR and you will use feldspar dating to date the older part of the Loess section. So a stringent preheat, so quite a high preheat of 300, 320, and a high stimulation temperature is what I prefer, or what is preferred generally for dating. So that would be my suggestion. It depends, of course, if you are having a site where you're only looking at late Holocene Loess, you will have to go to more bleachable signals of post-IR 180. But generally, you use feldspar to date old materials, so then you need to use more stringent preheats. Let's now see. Two commonly used post-IRSL protocols are, as I said before, two-step procedures or multi-elevated MET post-IRSL protocols, and there are many variations published, and some they use only 50 degrees here, sometimes you use higher temperatures. But the difference is that here in MET protocol, on one aliquot, you make all successive higher temperature stimulations to reach in their plateau method a more stable signal, whereas here you do all of this in one go. And it's up to the user to decide which one he or she would like to use. There are some There's some guidance on protocol parameters that I would like to mention here. For two-step post-IR methods, you would do first IR stimulation plateau, and that's shown here in the black circles here. So as you can see, for this older sample, the lower temperature, 50 degrees or 80 degree first IR stimulation is apparently not enough to get a stable signal. And whereas if you would take the young sample, it would probably be completely flat, and you could take an IR 50 before the 290 stimulation, for example. So first IR stimulation temperature plateau is what I would suggest. And with MET, they will. It's advocated that you should see some leveling off here at the top part of your plateau, where you don't see any significant change between the upper temperatures, and then they claim that you have reached a stable signal. So that's two different ways to look at in their way stability. Now, how do you choose them? Dose recovery is again the key performance test, and mainly for old samples, you would bleach your aliquots in solar simulator or in sunlight, and then you subtract the residual dose. So what do I mean by that? You prepare two groups of aliquots, you bleach them all down. One group you will measure the residual dose on it, because it won't be completely empty no matter how long you bleach. The other group you give the beta dose in your lab, and you measure that. You subtract from the measured dose your residual dose, and you divide it by the given dose, and that's going to give you a dose recovery ratio. For younger samples, you typically will add a dose on top of a natural dose, and then subtract the natural dose from your measured dose, and that's going to give you a dose recovery ratio. Be careful for the test dose size. Small test doses can sometimes give you trouble. You can get stuff in saturation very quickly. Your growth curve shape might change. I never use with feldspar test doses less than 30%. I mean, very often you go to 50%, sometimes even 100% gives you the best dose recovery. So I think dose recovery and test dose size is something that I typically play with to get the best protocol for my samples. Now, one thing I should also mention post-IR IRSL dating is that you have this some kind of hard to bleach component, or very hard to or unbleachable residual, as we sometimes call it. That needs to be subtracted prior to age calculation, and this is there are two ways to do it. You can use a solar simulator. So this is shown here by Yi et al. You have three samples of different ages, and then you bleach them down for, say, like half a year, and you can see an older sample has a bigger residual in the beginning, but after very long bleaching times, you seem to be getting them all to a quite stable level, and that's shown here. The intercept on these curves here for different bleaching times is plotted here to the right, and as you can see, after about, I would say, a week or 2 weeks bleaching, you're getting this constant residual of about 6 gray here. But I don't know if you would bleach 2 or 3 years, if it would do another drop. We don't know that. So another way of looking at this is, if you have the chance, if you have the possibility, is to compare just your feldspar ages with quartz ages, shown here in this paper and also in this paper. And then you see you'll consistently get an offset of your feldspar against the quartz ages here. And this intercept here gives you some feel for this unbleachable or hard to bleach residual. So you get an age here, and then you can multiply by your typical feldspar dose rate for the site. And in this case, it will give you a dose of about 5-6 gray. In this case, it's about 15 gray. And interestingly here, you can see after about 50-60,000, your feldspar gives older ages than your quartz, and this is probably your quartz OSL signal getting into saturation, so giving age underestimates. But as a rule of thumb, these residuals in Loess are typically 5 to 20 gray, based on the papers I've quoted myself, and also published in the literature. And this will be the same also for MET signals. Once you're reaching this 250, 300 preheats, 320 degree preheats or stimulation temperatures, you will get also residuals of this order. Now, some studies, some very nice paper here by Zhang et al. In 2022, an MET approach with many, I don't know how many tens or hundreds of ages they have here. And an interesting feature here is they can date back to 300,000 years. I personally only have successful two-step post-IR dating back to a little bit below S2 using SAR-based method. And also they show here that when you do pure SAR, you begin to underestimate the expected ages. When you do the MAR, so multiple aliquot regenerative dose method, you seem to get ages back in agreement. And that's quite an interesting feature that I don't still fully understand, but it appears that resetting by heat in SAR is definitely not the same as doing a solar bleach prior to giving a dose in a MAR approach. So it appears the MAR regen growth curves match closer your natural dose response curve. And that's an interesting piece of work we should all be paying attention to. Now, another study, and I will go a little bit quicker here. This is from the southern part in Siberia, close to Novosibirsk, the Loess site. It was quite controversial, the data at first, because they attributed this to be marine isotope stage 3 soil in the beginning for many, many years, and then this was stage 5. But as you can see, it's clear that you have stage 5 here, and this is stage 7 soil here at the bottom, with a huge gap sitting here of about 90,000 years. The paper has just come out, or is going to come out in the next couple of days. What I'd like to mention also here, when you interpret data from soils, be careful. Here we dated to about 150,000, which is essentially you're dating the Loess deposition. You're not dating the soil formation process. You're dating when the Loess was deposited there. And this is just an alluvial horizon that you could say, okay, well, my age is overestimating. It's not. It's actually you're dating the last time sediment saw daylight when the Loess was put there, and the soil overprinted the Loess there. Now, short mentioning on Bayesian modeling and detection of discontinuities. So as we all know, once we have our ages as a function of that, we need to constrain to some kind of a model. And there are many models around there in the literature. And I'm certainly not an expert on statistical modeling, or I'm more a user. But basically what it does, these Bacon or Oxcar models, it uses the stratigraphic information to constrain the fit. Basically, the principle of superposition, a younger sample will be higher in the sequence than an older sample. And that's going to help you. They have ways to constrain your fit in this way. And this is an example shown here. This is the Bayesian model through 6 data points from the Jingbian site that I selected. Equally spaced. This would be done in the past quite frequently, only 6 samples. But now if you double the number of samples, you still get quite a nice fit that I put through. But then you have this outlier here, and it's okay, well, okay, 1 out of 12 that is out of the error envelope. I'm not too worried about that. But if you then do what we did in that, you take 55 samples, you can really clearly see that there was a big break here. So I would advocate for taking a lot of samples, because it's gonna help you to really exploit fully your Loess record there, and you would actually have made a mistake if you had only taken 6 or 12 samples there to interpret that record. So high sampling density needed for discontinuity detection. I will skip this slide. Basically, it's something I give to my students to check luminescence ages in the literature. First of all, independent age control, old technology, new technology. How is your quartz? What is the upper limit? Are they using it beyond these upper limits? Yes or no? Most of you know all of this. Now, what I would like to advocate for is where the Loess community and luminescence community could come a bit closer, because it would be nice to have more of these natural dose response curves, so we can really begin to understand what is the stability of all the signals we're having, what is the age range of different signals, and also how do different grain sizes behave for different for the same signal. So suitable sequences exist in China, and Loess 1 has been mentioned multiple times, but also in Tajikistan, where I'm also going to do a bit of work on now, in Serbia, deep sea cores. One of the questions we could address, for example, is this natural dose response curve shape the same for different regions? Is there like a universal natural dose response curve shape? That's something that could be worked on in the future, and that's quite interesting for us in the luminescence community to know. And to now I've summarized the different kinds of natural dose response curve works that have been done in the literature until now, and maybe I missed one, but I hope not. And as you can see, there's still some some question marks about this because, for example, in Costinesti, we get a poor match for 63 and 90 between natural and lab curve, and in another site in Serbia, we get a good overlap to 250,000 years. So there's still some things we don't fully understand. We could also address, can we use T2SL in other regions? What about Tajikistan? What about Serbia? And feldspar, we have a lot of work done on coarser grain feldspars, a little bit here on 4 to 11 micron, but not on Lodge 1. We are now working a little bit on the fine grains in Lodge 1 to look at the post-IR signals, how they perform there. And we seem to be getting up to about 300,000 years typically in feldspar dating, but then here in the Serbian side, only up to 400 gray. So there's still quite a lot of question marks that could be addressed. And so we have come far. There have been really advances in luminescence chronology and understanding, but there's still more to go. And then another signal that is also being looked at a lot more in Loess is the ESR signal. But there are apparently some problems with stability and also bleachability of the different centers. And that this is also an interesting work that has been done by the group in Hanover and also in the group in Romania. So some practical suggestions. I'll go a little bit faster because I'm definitely running a little bit out of time. And many closely spaced large luminescence samples is what I would suggest you take. Is there datable C14 material at the top? What about the water content history? And this I didn't address enough, maybe, but where's the groundwater table? Talk to the local expert in the field. Has it always been there? Has it been higher? What is the precipitation and temperature history of the site? Are you sampling in a gully? Is this a recent gully? Because if the gully was not there, say 100 years ago, your samples may have been a lot wetter than you, throughout their burial time, they may have been a lot wetter than what you're seeing now, or what you're thinking now. Is it a clay layer that may cause a perched water table? Try to measure some good present day and saturation water moisture contents, because they can give you a bit of a feel for, can give you a range of values to constrain your lifetime average water content. So instead of just guessing a value, it would be nice to get some good samples for this. Overall, try to combine quartz and feldspar dating. The top part, quartz, is going to be the most useful one, and feldspar up to 250,000, perhaps even 300,000 that we have seen before, and you will want to do a Bayesian HDAP model. So in summary, independent numerical chronologies are really crucial to fully exploit the Loess records. High sampling density gives detailed HDAP models and allows you a lot of things to be discovered and to be calculated. And I hope that we will be able, in our community at least, we will be able to do more work on natural dose response curve for different Loess regions and also for different signals and different grain sizes. So that's my I think my future, that's the future perspective I would like to give here. And then I would like to thank you for your attention, and I also apologize for taking too much time.
Thank you, Jan-Pieter, for this great talk. I think it includes not only the recent advances in luminescence dating, but also very details about how we do the experiment and analyze the data. You also propose some future research directions for us. I think this basic knowledge about the technique and protocols are very important for us early career researchers. And I think it is exactly the purpose of this workshop. So sorry for the Zoom meeting limit. We didn't not expect there are so many participants. So far, we still have like 173. We have extended the Zoom at the moment. So I think Aditi is also here. I think you should take over the chair. Aditi,
okay.
For that.
Can you hear me better now? My apologies. Thank you, Jan-Pieter, so much. This was a really fantastic talk. I'm sorry I missed the beginning. It was about the Zoom limit that Joey just talked about. I logged out and I could not log in because of maximum capacity. I now open the session for questions. So if anybody has questions, feel free to unmute and ask your questions, or if you would like to type it in the chat, you can do that and we can read it out for you and ask the questions as well. Okay, so by the time people are... Kaya, I can see that you put your hand up. So you have a question, yeah?
Hi, UP. Sort of one hopefully fairly easy question and sort of second on these advances. First one, if you could maybe talk and expand a little bit for people, because we have quite an extensive audience that are doing masters and even undergraduate studies, so they might not be as familiar. So if you could expand a little bit more about why we're going for 4 to 11 or 63 to 90. So why do we sort of missing out that middle part? So if you could expand on that, that would be fantastic. And my personal question would be, do you think there may be a relation between provenance and the sort of those response curve that we're seeing in quartz when you're proposing the sort of potentially like a regional response, but could there be something else to do with provenance, and maybe we can sort of start looking as a potential provenance change indicator by looking at those comparison between the natural and those response curves.
Mm-hmm. Yes. Yes. 4 to 11 or 63 to 90. This is also historically grown. You know, you can use coarse silt also, say 35 to 50 micron or so on. The only thing you have to be careful about there is that you may have some alpha contribution, because you won't really etch with HF for like 40 minutes, or so you will have an outer rim of your quartz grains that have had some alpha penetration. It will not be huge. It will be contribution 4 to 11 micron grains is about 30%, but I would suspect that you go coarser. I would not suspect this, so that if you go coarser grains, it will be less, maybe 15% alpha contribution. We would have to do the calculations, but it's more convenience why people use 63 to 90 micron or even higher grain sizes. And also, fine grains are problematic in some ways that the growth curves, they keep growing somehow. And this is a work that Alida Timar and her group have done in Romania, worked on for many years. And we still don't fully understand this fine grain shape. Maybe it has to do with alpha radiation, maybe some, but I think I would suggest to people who start now, try to take big enough samples so you can get coarse grains out, because it simplifies dosimetric calculation. You can just forget about the alpha component, but coarse silt should also work. You just have to be a bit more careful that you need to incorporate a certain alpha component there. It is not very difficult to do, but yeah. And then I don't know if that answered your question well enough. Yeah, and then about provenance, to be honest, I don't know. I really don't know if I think for quartz we will see different shapes. I'm quite certain. That's also what the evidence that so far been published is pointing us out to, that you have different natural dose response curve saturations for different quartz grains, and it may be related to provenance. But we would have to find a link there and to say, okay, there's a very clearly different a provenance feature for this kind of sediments than for the others, and it remains to be established, but it could well be real. Yeah.
Thank you.
Oh, great. Do we have any other questions from the audience, or if they would like to type that in the chat? Yeah, okay, Jiangwu. Yeah, you can unmute and ask your question. We cannot hear you because you're still muted.
So can you hear me now?
Yeah.
Oh, thank you, Peter. Thank you for this talk. Yeah, I'm doing some research about the violet laser luminescent dating of some very old Loess. Yes, and I have to say from your talk there, you have do some summary of the VSL dating. So can you introduce more about the recent advances about violet laser luminance dating?
About violet stimulation?
Violet laser luminance dating.
Yes. Yeah.
Because I see some paper from you and Christina Angard. It's very good. Do you know more recent advances about that? Can you introduce
me? I have not done any more work on VSL since then. So, and together with Christina Ankergaard. So what's in there is what I know. Other groups have also been looking at VSL and doing some good work. The big problem with VSL is, I think, to measure with SAR. Yeah. So maybe one of these multiple aliquot regenerative dose techniques will be better by bleaching down in using solar simulator and then building your curves there. That's probably the next attempt that should be done in VSL. But I have no good concrete suggestion for you now apart from that SAR is problematic. And it probably has to do with the heating after your test dose, that you don't come back to the right situation before giving the next dose.
Oh, all right. Really thanks to you.
Yeah.
Okay, do we have any more questions that people would like to ask?
Hello, Dev. I want to show my recent work and have some questions related want to discuss.
Yeah, sure. If we can just do this after this question session, and we can then open it for presentation as well. Yeah.
Okay. Thank you.
Yeah, not a problem. Do we have any further questions? I would like to quickly ask one, if there's still people thinking about it. It'll take you a bit on the side, but I was wondering about TTOSL and its applications for extending the limit of dating quartz, basically in fine-grained sediments. Because there was a huge discussion, I think in one of the conferences or something, I saw people discussing about TTOSL and its application to fine grains and coarse grains, and which one was better, giving a better signal. And it somehow also depended on the sensitivity of the quartz. I don't know, what do you think about the potential of TTOSL for dating quartz, like beyond the upper limit of what we have right now with the SAR protocol?
Yeah, I think it still has potential and significant potential, because you're having a natural dose response curve. I think it's saturated at like 2000 gray or something, 2200 gray. So the signal is there to get up to say 700,000-800,000. The problem is you have this lifetime problem, that it's thermally unstable. So I'm quite sure we'll have to do something with the correction for the lifetime.
Okay.
That I'm quite sure that this will be needed for most samples, for nearly all the samples that you want to try to date with TTOSL. So far, I have not been convinced that it's helping us so much further out, but it's very interesting. I've also been thinking of moving on to TTOSL myself if there's a time. But there's definitely this problem of thermal stability and in 4 to 11 microns. I know that in Australia, like the group Lee Arnold, they can when they do look at single grains, basically coarse grains, he can identify more thermally stable, more stable T2SL signals and use those to date. So I would suggest you look at the papers from Lee Arnold, where he's been successful in trying to get good T2SL ages, because he can pre-select the grains by doing some thermal stability testing in the lab. He can identify those grains that are most stable and use those for dating. I fear that in Loess it's not going to be possible because it's so fine-grained. You can't get the coarse grains out. That's one approach that could be done. Another approach will be to have to correct your ages for lifetime. Stability, yeah. That's and I don't know in Loess. Maybe you guys know the literature probably maybe better than I do. Is that that for how much? I think mainly fine grains give T2SL And there's no, and it's very variable where you see T2SL signals. Some samples, they don't give anything at else. You need bright OSL, and then you get you have the chance to get some T2SL out. How universal it is, that remains to be established.
Yeah. Okay. Yeah. Thank you. Yeah. So it's currently under development. There is still potential. Yeah. Definitely. Yeah. Okay. Do we have any more questions? And if we don't, there's so many people that I have to slide through the entire list to see if there are any questions. Well, I guess then we can just further move on, and I will now open the session for the presentations. Thank you, Jan-Pieter, for the excellent talk, for answering all our questions. And with me currently, I have two people who would like to present their work. There is Yin Wang and Jiang Wu. So we can start with Ying Wang, who will present her research work. So if you can share your slide or your screens, Ying, and then you can start.
Hello, can you hear me?
Yeah.
Okay. Let me. Jan-Pieter's lecture is very wonderful, and I learned a lot from this. And I want to show my work and have some related questions to consult you. First, hello everyone. I'm Wang Ying from Nanjing University. My advisors are Xu Zhiwei and Yi Shuangwen. The topic of my short presentation is the luminous dating of young sediment from Tangle Desert, comparison of coarse OSL and K feldspar PIR ages. And we in the present study, we dated young sediment from the Tangle Desert. Both coarse and K feldspar fractions was extracted for luminous dating. The course used SAR protocol and the key feldspar use the post-IR ISL protocol. We also carried out a set of tests such as the dose recovery test, fading test, and a residual test. We can see from the picture that the decay curve, the growth curve, dose recovery ratio, recuperation, and recycling, of course, was relatively good, indicating that our test procedure was reliable. It is the same with the key feldspar. By comparing the decay of coarse and the key feldspar, we find that the core signal of the NGU, this one, 3665, is very weak, almost close to the background, indicating that the dating result of the course for sample may not be accurate. The age is about 115 years. And the key feldspar may have greater potential due to its higher signal sensitivity. We also do the G-value test. The G-value of PIR is less than the G-value of IR. And the result shows that the uncorrected PIR ages are in good agreement with the coarse OSL age, while the corrected PIR age are generally overestimated for about 2 to 5,000 years. And I have the following two questions. First, for example, the weak core signal of 3665 may lead to inaccurate dating ages. Although the key feldspar can obtain relatively reliable results, there is a lack age verification. I want to ask if there are any better dating method to verify the reliability of the key feldspar age. And the second one, although the G-value of PIR is smaller than that of the IR, the PIR G-value varies very big from smaller than 1 to near 3. I want to consult whether it is necessary to correct the age for relatively young samples. That's all. Thank you.
That is great. Thank you for your talk, Ying. Does anyone have questions or suggestions on Ying's talk? We can quickly talk about her work. Yeah, Peter.
Yeah, you can still hear. Am I muted? No, I'm not muted, right?
Oh, no, we can hear you. Yeah.
So on the very young sediments, I am not completely certain what the problem is, but one thing, you're saying inaccurate dating, it's probably you're having a lack of signal there. One thing you could do, and maybe you have tried, is to make sure you optimize your detection. So make sure you don't have any grease on your quartz window, that you have a large aliquot. Also use a very large test dose, because you really want to get all the photons you can get to date this very young Loess, these very low quartz ages. Very small quartz doses to measure them. You really need a very sensitive piece of equipment for that. So that's something that you could optimize also. So I don't think these were small aliquots, right? They were probably large aliquots. So there's not much more you can do. But the test dose is certainly something to look at. That is big enough, because the natural signal you can't do anything about. If it's so young, it's going to be small, and that's going to give you scatter anyway. But you can improve your precision by getting a slightly bigger test dose. You get at least the lab curve constrained very well. And then you can also play a little bit with early background subtraction. So integrate a little bit more of your quartz and take a little bit further background, so you can get your precision a bit better there. That would be my suggestion. And then the second question on the G value on post-IR 150 for something that's 15,000 years old, I'm not surprised that the G value is not necessary. G values are tricky, and I don't think they mean so much all the time. So your quartz is what you need to go by here. Your quartz ages are the ones that are accurate, and if the G correction is wrong, that we've seen this before, that you don't need to fade in correct your post-IR 150 signal.
Okay.
That really my comments on this. Yeah.
Thank you. Now I have a better understanding of the luminous dating, and I learned a lot. Thank you again.
Are there any other questions on Ying's talk, or any suggestions for her to try? Yeah, okay, so I will just ask you quickly, just because it's a very interesting area of the Tenga Desert. On the map, you showed that you had a lot of sites in the desert area that you were looking at. Yeah, so they're spread across basically. So you see a change in sensitivity of quartz in the different samples that you've taken? Because you said you had low sensitivity for some of the quartz. So do you see like a spatial change in sensitivity in the desert area from your samples? Maybe some quartz have higher sensitivity or lower sensitivity?
From our results, we can see coarse OSL have a lower sensitivity, and the post-IR have higher sensitivity, especially for the site XJZ. This sample is very young, and the OSL sensitivity is very low, and the signal is very weak, and almost close to the background. So I think the XGZ is XGD. The sample from XGD is very weak, and among our samples, some of the samples sensitivities is higher, and I think it may related to the environment or and other reasons. different sites have different sensitivities. Yeah.
Okay, yeah, that's interesting to know. Yeah. Okay, yeah. Thank you, Ying, for this for the presentation of your work. It's really interesting, and I hope you get some good ages soon. Do we have any more questions? If we do, then you can unmute and we can ask questions, or we move on to, I guess, the second. So there is a question in the chat. It says, hi, could you please let us more about the G value when it comes to post IRs? I guess it's for you. Yeah, Peter.
Yeah. It's a tricky question. I'm not a fan of G value correction, I must admit. And I think many studies, at least when you go in, it depends on how stable, how old your sample is. So if you date something that is let's say 100,000 years old, and you have you measure with post-IR 180, you will have to fade in correct. But I don't think it's necessarily going to give you the right fade in correction. Whereas if you then use a more stringent preheat of 320 and a post-IR 290, it's very unlikely you're going to have to fade in correct. And even then, you will get a certain G value measured in the lab, and it will maybe be 1.5%, maybe 1%. It may be quite similar to your post-IR 180 fading rate. And that's where the problem lies. So when dating young stuff, I would also not fade in correct my post-IR 180 or 150 samples. And that's where the comparison with quartz is quite crucial. That's a nice part we've seen from the previous presentation here, that she shows that. Yeah, C14. Okay, this is the next question, but maybe not related to this. So basically, try to, the older you're going, more stringent preheats, higher temperature stimulations, and unlikely you're going to need fading corrections, even though you'll have finite fading rates in your lab measurement. But some people disagree with that. I mean, I'm not saying that this is the truth for everything. But younger samples, then you can afford to go lower temperature and also not fading correct. That's my view. But you need to check it with, say, quartz OSL or with, as we've seen here, C14 ages or so on. And I don't know if the next question is also for me about C14 and lead-210. Lead-210 can only get you to the last 100 years or so. So it's like half-life of 20 years. So this is really, really historical stuff you're going to look at. And actually, I think quartz OSL can compete there if you use a low preheat. So say preheat of 160. So you don't have any thermal transfer, and you have well-bleached low-sig material, well-bleached aeolian sediments. I'm quite sure we can date with quartz something that's 50 years old. And of course, C14. And actually, C14 at these very young ages has a problem with the calibration curve. So maybe your best bet is there, quartz OSL. So this was the next question I commented on. I hope.
Yeah, well, I think everybody saw that question. Yeah. So thank you so much.
That's okay. Hope that's
yeah,
okay.
no, absolutely. Yeah. So yeah, I think since if there are not more questions, and since we're also running a bit out of time, and we have another presentation by Jiang Wu, and he will be talking about violet stimulated luminescence dating. So yeah, you can feel free to share your slide and start your presentation. Yeah, we don't hear you. If you have to just unmute yourself.
Yeah. Can you hear me now?
Yeah, perfect. Yeah.
Yes, it's very honorable to present my work here. I just want to share a brief presentation about my preliminary study about violet laser luminescence of Loess. Sorry, I can't slide it. Oh, it's okay. I'm Jiang Wu from Nanjing University, and I'm now doing some tests about the Loess of southeastern margin of Lower Chinese Loess Plateau. From the fieldwork, I think our sample is depleted on the top for the S1 and deeper is L2 and it's very continuously. But then when we test some geomagnetic results, but we find it's very interesting that we find the BM boundary at not very deep, and it's about 14 meters degree. So we think it's very strange. And we correlate the geometric and magnetic susceptibility curve to the Loess sequence, and we find it's very good correlation. We find boundary and the curve peaks is very good correlation. So we think the first layer is that S1, this there S1, or is not S4, S2. So it's very important. It takes us to a question that the sequence lacking Loess depletion from L1 to L5. Then it's very important to give some independent age control. So we take 11 samples from 1.5 meters to 11.4 meters. So, and now we have done the test for the first sample. So the estimated ages should be around present to 130 kilo years or to 500 kilo years. And we do some tests with the commercially quartz SR OSM dating and quartz TTOSL dating, even with more feldspar post-IR IRSL dating. I think we see from this case graph that those response curve almost likely be saturated. So we think only that sample is older than all this research. Then we try to do the vessel testing when we use the SAR method. The result shows that the SAR gave us very good recycling ratio, but this with a very high recuperation, almost 22%. And if it is about 83 grays, and then we try the vessel much adequate additive dose method, this result gives us a good DE about 100 or 1056 degrees, but if there's a big scatters between the different disks, and also if we check the probability error, there is a very large error bars. So, and we do some bleaching test experiment. We find there is a very good, a big residual signals for about 20% if after 3 days sunlight exposure, and with violet laser stimulation, we have some residuals from 23% to 16% with 200 seconds or to 10 hours. But our results is quite different with other research results, because you see with this, certainly bleached with sunlight and it's bleached to almost to zero, but my results still still higher than 16%. And even with violet laser bleach, my sample bleached very fast after 200 seconds, but Vanguard played that they show that it's close to nearly half of this initial signal even after thousands of seconds. So this is a very big difference. And if we summarize all the dating results, we can find the upper quartz SAR and quartz TTOCL, polymineral post-IR and feldspar post-IR, that they're all saturated. But if we check the VSL results, we can find those response curves are not saturated, and the quartz VSL MAD method gave a very good DE results, which is to tell us the suggested samples can date back to S5 and SS2. It's about 550 kilo years, and at least with the saturated response curve of the quartz and feldspar we can know that the first layer is much older than S layer or S1. And that's the very quick summary. We tell that this Loess and polycyclic sequence appears to lack of Loess F1 to F5, and the bleaching test VSO signals show initial signals are reduced to 23% with 200 seconds of wireless duration and drop to 16% after 10 hours. And there is still 20% of the initial signal after 7 days sunlight exposure. The SAR result of VSO may have age count underestimation, and particularly, and the possibility, the primary is that there is a high level of recuperation. Also, the VSO MAA result shows some big potential to take Loess back to 550 kilo-year. Even if we test the 2D naught value, perhaps it can even date back to older than 700 kilo-years. And our work is very preliminary, so I really sincerely welcome your suggestions. Thank you.
Thank you for presenting your work. It looks really interesting and very, very promising. Any comments on this presentation that anyone has? I can ask you a quick question. This is just out of curiosity. Is there another independent age control on this site to verify if the ages that you're getting from VSL are what you expect them to be?
We can get some estimated age from the magnetic exactly quality and magnetic paleomagnetic, but for right now there's no other independent age control.
Okay, and are there any other samples you've tried at the site, or is it just?
For right now, I just test the first sample here.
Okay. Now this looks really good. Yeah, thanks.
Yes. Could I say a few sentences to your questions, Attic? Yes. As you know, the Chinese Loess paleosol sequence has been quite well established, and this site is located at the basin in the East Qianling Mountains, where we also have found a thick Loess deposit, and we can compare the stratigraphy, especially in the lower part, with the typical Loess paleosol sequence in the central Chinese Loess plateau, where several people have mentioned the site. So that is another evidence to constrain the ages of the sequence. And indeed, in the last month, we visit the site once more. In the last year, we think the upper part may be S1, S2. But now, if you compare the Loess stratigraphy with the typical Luochuan one, and also as Wujiang said, our paleomagnetic stratigraphy and other several deposit process evidence can say the upper part of the sequence has been removed by water erosion, I think. And also, I think the Wujiang's results is very, very good. It can be compared with other geologic evidence. That's my comments. Thank you.
Yeah, no, it looks really good, and Chinese Loess is probably the world's most studied Loess deposit. So it's really good to have that to compare to other stratigraphies for sure. Yeah. Any other comments on violet stimulation or its what other potential methods that could be tried? Well, okay, then if there are no further comments about the presentation, I would like to thank Jiang Wu for presenting his work. It looks really promising. And since we're also towards the end of our time today, for this session, I would like to say that we end the session for today here. And I would like to thank Dr. Jan-Pieter Buylaert for his excellent presentation today and for taking the time for being here with us today and presenting his work. I would also like to thank Professor Shilin Yang as well as the Inqua Committee for supporting the ECR workshop. And lastly, thank you everyone for being here today and for joining us. And we hope to see you all for tomorrow's talk for another great session on provenance studies by Dr. Pieter Buylaert. And yeah, Jouet, would you like to add some comments to that?
Oh, it's okay. Thank you. Thank you, Jan-Pieter, especially for this great talk, for your time and for your effort.
Thank you.
And thank you everyone for joining us. So we will meet tomorrow.
We meet tomorrow.
Yeah,
see you.
See you.
Bye. Thank you.
Yeah, see you.
Thank you. Bye. Thank you.
Thank you.